my name is Xinping. The topic for my video project is spin qubit orbit. In particular, the paper I read is about circuit quantum electrodynamics with the spin qubit. Before I jump into the details of this paper, I'd like to give you a general idea of what's going on we talked about in this paper. So, from previous work, we know that two-qubit operation is only realized in nearest neighbor exchange coupling due to the weak magnetic moment of electrons. In this paper, it manages to achieve long-range spin coupling via superconducting microwave cavities in circuit quantum electrodynamics. Here I have the keywords listed here. The first one is single spin qubit device, and we have spin blockade, which is specifically for the readout, and then we have electric dipole-induced spin resonance in quantum dots, abbreviated as EDSR. This is a similar but more complicated version of ESR. So we are trying to introduce the electrical control of the spin orbit qubit in EDSR. And then I have spin orbit qubit in semiconductor nanowire. In particular, the material we are using now is indium arsenide. And then the last one also is the most important one, is about circuit quantum electrodynamics. So for the background of this paper, I would like to talk about the single spin qubit device first. I think we are already very familiar with this topic. So here we have the microwave transmission line shown in the upper left portion. The donor is subject to an oscillating magnetic field B1 from the transmission line, which is perpendicular to the in-plane external field B0. We have this stationary magnetic field B0, which drives the Larmor frequency. And after we switch the frame and we apply the oscillating magnetic field B1, we will have this Rabi frequency. And then for part B, I would like to talk about EDSR. It plays an important role in the qubit state transition for the readout. Here we have the schematic of the setup for E-field control of spin via the spin-orbit interaction. The quantum dot QD contains a single electron with spin s equals 1/2 deep in the Coulomb blockade valley. The gates 1 and 2 are used to generate an alternating E field, which acts via the spin-orbit interaction on the electron spin. As a result, we have the EDSR occurs if the frequency of the E field is tuned to match the Larmor frequency. So here I have the theoretical background for the E-field control over spin orbit qubit. If we look at this equation, H is the total Hamiltonian, which consists of 4 different parts. HD is the Hamiltonian for the confined electron. HZ is just the traditional Zeeman interaction. HSO is for the spin orbit interaction. Here, the V, the potential, is a small perturbation term indicating the electrical potential experienced by the electron. In our standard ESR scheme, an alternating magnetic field is generated by a current in a nearby conductor. However, in this setup shown in the figure, no charge flow is ideally present between the gates. However, the alternating electric field gives rise to a displacement current with the current density shown here. The external magnetic field would thereby acquires an extra component which would change with respect to time. And then I would like to talk about the spin orbit qubit in a semiconductor nanowire. Here we implement spin orbit qubit in an indium arsenide nanowire, where the spin orbit interaction is so strong that spin and orbital motion can no longer be separated. Nanowires offer various advantages for quantum computing. They can serve as one-dimensional templates for scalable qubit registers, and it is possible to vary the material even during wild growth. Such flexibility can be used to design wires with suppressed decoherence and to push semiconductor qubit fidelities towards error correction levels. In figure A, on the left side, it shows an image of our nanowell device. Two electrode source and drain are used to apply a voltage bias across the nanowell. Voltages applied to 5 closely separated gates underneath the nanowell creates a confinement potential for 2 electrons separated by a tunneling barrier. Similar to pure spin states, a magnetic field B controls the Zeeman splitting. The crucial difference is that in the spin-orbit qubit, the orbital part of the spin-orbit wave function is used for qubit manipulation. So if we look at figure B on the left, we can see that a microwave frequency electric field applied to gate 4 oscillates electrons inside a nanowell. This motion can induce resonance transition between spin-orbit states by means of EDSR, which I talked about in the previous slides. At a resonance, the spin-orbit state of the double dot rapidly changes from parallel to anti-parallel. So if we look at the figure B on the right, we can see this transition. So the anti-parallel state cannot experience spin blockade, so the left-hand electron tunnels to the right, thereby contributing to a current. Figure C on the left shows the resonance as a V shape that maps out the Larmor frequency in the plane of microwave frequency and a magnetic field. If we look at the higher magnetic field, the resonance line splits indicating that the G factor in the left and the right-hand dots, GL and GR, are different. This is expected for quantum dots of different sizes because confinement changes the effective G factor. So for the last part, I'd like to talk about the circuit quantum electrodynamics. This is the most important part because it explains the interaction of light and matter. As in the field of cavity quantum electrodynamics, a single photon within the single mode cavity coherently couples to a quantum object, such as an atom. In contrast to cavity QED, the photon is stored in a one-dimensional on-chip resonator, and the quantum object is no natural atom but an artificial one in our circuit QED. Usually, we would choose to use the Cooper pair box for the circuit QED because of its large effective electric dipole moment. The resonant device used for circuit QED are superconducting coplanar waveguide microwave resonators. Coplanar waveguides shown here in part A consists of the signal carrying center line flanked by 2 grounded planes. The electric field is basically confined between the center conductor and the ground planes, resulting in a very small mode volume, which gives rise to a very high E field per photon. The full quantum description of the matter-light interaction is given by the equation shown here. The 3 terms can be ascribed to cavity term, which is mimicked by a harmonic oscillator, an atomic term, and an interacting term. The resonator can be modeled as a parallel combination of the capacitor C and an inductor L. In this formulation, omega R is the resonance frequency of the cavity, given by 1 over square root of LC. A dagger and A are photon creation and annihilation operators, respectively. The atomic term is given by the Hamiltonian of the spin 1/2 system, with omega A being the transition frequency for the Cooper pair box, and sigma Z is just the Pauli matrix. The operators sigma plus and minus are raising and lowering operators for the atomic states. And here we have the detuning, which is usually represented as capital delta, as the difference between omega A and omega R. The strong coupling between the fields in the resonator and the CPB can be used to perform a quantum demolition measurement of the state of the CVB in the non-resonant or say dispersive limit. In this setup, the CVB acts as an effective capacitance which is dependent on its sigma eigenstates, the coupling strength G and the detuning delta. This variable capacitance changes the resonator frequency and its transmission spectrum. Such shifts in the resonator frequency are sensitively measured as the phase shift. And this phase shift can be represented as arctangent of 2g squared over kappa delta. Kappa is the permittivity of the medium. Finally, with all those information borne in mind, we're going to move on to the paper about the CQED with the spin qubit. This paper basically just combines all the ideas I talked about in the background to achieve long-range spin coupling via superconducting microwave cavities in circuit quantum electrodynamics. So here is the diagram of the hybrid device design. The CQED allows spatially separated superconducting qubits to interact via a superconducting microwave cavity that acts as a quantum bus, making possible two-qubit entanglement and the implementation of simple quantum algorithm. Here, we're trying to combine the CQED architecture with spin qubits by coupling an indium arsenide nanowire double quantum dot to a superconducting cavity. The architecture allows us to achieve a charge cavity coupling rate of about like 30 megahertz. Although electron spin states cannot be coupled directly to the electric field, as I have mentioned in the background part, the spin-orbit interaction enables electrical control by perturbing the orbital component of the wave function. In this paper, so it basically just takes the first steps towards realizing this approach and couple the electrical field of the high-quality vector superconducting cavity to an nanowire. Such electric field is generated through the photons in the CQED architecture. Here, if we look at the part C, we can see this epsilon naught, which is just the electric field in a CQED architecture. So this paper also provides the detailed measurement cycle. So the double quantum dot is put in either the up-up or the down-down speed configuration as a result of Pauli spin blockade. But EDSR transition can lift this blockade, resulting in current flow through the device. In particular, we combine the quantum control of the spins using EDSR and cavity detection of single spin dynamics using the pulse sequence shown in figure B on the right. Starting with the spin qubit in state up-up, we pulse to negative detuning and apply a microwave burst of length tau b to drive EDSR transition. For example, an EDSR pi pulse will drive a spin transition from up-up to up-down. Figure 1c on the left is the energy levels of the spin orbit qubits. So from those data, it demonstrates coherent control of the spin qubit and readout via the cavity by varying the EDSR microwave burst length tau b. Figure E on the right shows the measured phase as a function of tau b and the gate drive power. These data here show how the microwave field of the cavity is sensitive to the spin state of the single electron, and that by using the CQED architecture, quantum dot spin states may be coherently controlled and measured using microwave electric fields. At the end of the paper, it provides a rough estimate that the spin cavity coupling rate is 4 orders of magnitude larger than the coupling rate that could be obtained by coupling a single spin to the magnetic field of the microwave cavity. It also proposed some methods to reduce the cavity decay rate or to decrease the qubit decoherence rate in order to increase the spin cavity coupling rate. It suggests that we could possibly replace the indium arsenide nanowell by other materials which require even larger spin orbit coupling. We could probably try nuclear spin-free germanium silicon core shell nanowells. Basically, the circuit QED allows strong dipole coupling between electrons in a high-quality superconducting microwave resonator. This technique can be used for sensitive detection and manipulation of electron degrees of freedom. Here, this paper presents the first realization of a hybrid circuit in which a large number of electrons are trapped on the surface of a superfluid helium inside a coplanar waveguide resonator. Since the quantized lateral motion states and the spin states of electrons trapped on the surface of superfluid helium have been proposed as basic building blocks of a scalable quantum computer, this paper is a great application of the circuit QED. So in this hybrid approach, electrons are trapped above an on-chip superconducting microwave resonator. The presence of the electrons changes the effective capacitance of the cavity, resulting in the dispersive shift of the cavity resonance frequency, which is shown in figure B. I find this paper very interesting because it achieves the coherent coupling of a single spin to a microwave cavity photons. This paper uses a circuit design based on a nanoscale spin valve. We coherently hybridize the individual spin and charge the states of a double quantum dot while preserving spin coherence. The scheme allows them to achieve spin photon coupling up to the megahertz range at the single spin level. In figure A, this shows the essential parts of the device. The resonator's central conductor is surrounded by ground planes that are open in a small region in order to place a carbon nanotube and the necessary DC lines to form a double quantum dot. In figure B, it gives us the atomic force micrograph of the nanotube with 4 top gates used to bring DC electrical potentials as well as coupled to the resonator via the potential of the gate resonator. So in figure C, we see source S and drain D electrodes. They're made out of a ferromagnet alloy. So the black and white colors correspond to north and south poles of ferromagnetic domains. So in figure D, it just gives us a general principle of our coupling mechanism. The proximity of the non-collinear ferromagnets induce a different equilibrium spin orientation if an electron is localized in the left or in the right dot. Photons are coupled to transitions, changing the localization of the wave function psi, and hence coupled to transitions, changing the spin orientation. Figure E just shows that the Bloch sphere of electrons being shown the different magnetic field contributions. In figure F, when the transition crosses or anti-crosses the resonator frequency, the associated susceptibility exhibits a resonance that is observable in the phase and amplitude of the resonator transmission. So basically, there are a lot of application of the CQED architecture to the spin orbit coupling. Here are all the references I used in this presentation.